You're listening to the Good Question Podcast with Richard Jacobs. Our goal is to make each of our guests exclaim, that's a good question. I don't know the answer. Because when that happens, it means you, the listener, may be inspired to learn more beyond the interview and to ask great questions yourself that lead to new insights. In this podcast, we cover historical and current anthropology, comparative religion, and history. Welcome, and let's get started.
Hello, this is Richard Jacobs with the Good Question Podcast. My guest is Fred Jordan. He's the CEO and co-founder of AlpVision and FinalSpark. We're going to talk about what's called Wetware. Scientists are using human mini brains to actually power computers. So it should be a very interesting topic. Welcome, Fred. Thanks for coming.
Thanks for inviting me.
Yeah, I'm familiar with organoids, brain organoids and all that, but those are, really simple objects. What are these mini brains that you guys are creating? What are they made of? How are they constructed?
Well, actually, no. The term mini brain is the term people use for actually brain organoids. In the science community, you would talk about brain organoids or different types of organoids. But mini brain is not really realistic because it's very far from a brain.
Okay, so these are organoids then?
Yes.
Okay, so you'll take like one type of brain cell and you'll culture them and it'll make like a sphere, or what kind of structures are they making?
Well, yes. Most of the time they will look like a sphere. Most of the time, I would say, okay? If they are not like a sphere, it may be a problem, actually. Or it may be that you are differentiating in many different types of cells, and then you have a guided differentiation. And this is also a topic of research, is how different types of cells do you want to have in your organoids and how internally it is structured.
Okay, so are you keeping it simple with just one cell type and very little structure, if any? Or are you doing multiple cell types?
We do both, actually. Okay. On one hand, we do simple ones, and the other one we try to make advanced ones.
Is it so you're having them power computers? Why? What's special about a brain that would power a computer better, faster, with less energy? What's the benefit?
Well, when we say power, we mean the computation. Okay. The power is not really a big power coming from the neurons. Okay, of course. So there are two things. Okay, the first one, the most obvious, is the power efficiency. Okay, your brain runs on 20 watts, but you have 100 billion of neurons, 10,000 synapses per neuron. If you wanted to make a simulation of this, that means basically run on a computer, a traditional computer, your own brain will take like a small nuclear plant, So
wow, is it so it's that complex?
Yeah.
So if you were going to recreate this in silico, it would take enough power to power a nuclear power.
It would use enough
use that much power, yeah.
So that you need a power plant to power your silicon-based simulation.
But somehow biology is doing it with 20 watts.
Yes, that's the intriguing part, actually. In biology, every neuron is actually a computer, okay? And when you do AI using simulations of neurons, but in order to simulate, 100 millions, like when you use ChatGPT, for instance, you are going to have in memory 100 million artificial neurons, but when you want to update them, you are going to transfer all this data and compute it in one central computers or as many computers that you have, and that's always way less computers, even on a GPU, than the number of neurons, which is not the case where the organic nervous system is using as many computers as number of neurons.
Also, our organic brain uses orders and orders and orders of magnitude more to little computers to establish the network. Is that what you're saying?
Well, yes. In addition, indeed, we have many nervous connections in our brain. Okay, 100 billion is really impressive. But if you multiply now by 10,000 connections per neurons, it's something. Now, there is a second reason why it's interesting, is that, people think about AGI, artificial general intelligence. Some people think that maybe LLM is not going to be sufficient to reach AGI.
Right.
And one approach, because there may be missing something. Okay. One approach to this will have a hybrid approach to AGI. When you have LLM on one side, so silicon-based, I would say it for the reasoning through words, I would say. And the organic part, which is based on Wetware, and both being integrated together. They integrate actually very, very well. Digital world and organic world like Wetware.
Well, right now with LLMs, it's the totality of, I mean, we don't get everybody, but it's like the totality of human thoughts on a particular subject. But the reasoning part, I would say, doesn't just only come from our experience, but we have, this is just me saying it, I don't know, we somehow have a sophisticated, apparatus that allows us to think. It doesn't seem like LLMs think, but they just explore the connections in the answer space of all the data that they've sucked up. But there's no like reasoning beyond it or on top of it. Is that right?
That's a complex question. Very complex, Of course, you're right. Okay. Basically, you are just doing interpolation in latent spaces. This is a general interpolator, artificial neurons, and that's it. This is, ChatGPT. Okay. In a nutshell. Okay. Very, very good. Are we way better than this? So for sure, we are not manipulating words when we are reasoning. Maybe we don't maybe need words. Actually, it's not even sure that the brain was made for thinking. Okay. The brain is actually made for reacting. Okay. And processing information, not thinking. So we don't feel that far superior to artificial neurons, which are made to agglomerate words. I think these are two different ways to process information, and both are which are very valid.
So, if we go back to the power consumption, by what factor less is power required or needed to run a human brain versus, doing it in silico? Is it like 1 million times less, or what's the factor approximately?
Yeah, 1 million is okay. It's typically the factor that you can find on some publications, like Professor Hartung published on this. And now, there is 1 million, this raw difference in power efficiency, correct? However, if you implement this for real, you are going to run into a number of technicalities which are going to consume some of this energy efficiency. And I think at the end, we'll be able to develop servers that will be maybe 100 to 1,000 times more energy efficient than the ones of Amazon Web Services, for instance.
Wow. So what's happening? Have you been able to experimentally hook up an organoid to provide computation for some kind of chip? And has it worked? Like, what's happened?
Well, we do it on a daily basis. Okay. We have thousands of brain organoids in our lab, and we put them on electrodes and we make them available for researchers across the world, and they access it remotely in Python. So they interact with them, and they work on programming it and send stimulations, read their reaction, deliver neuromodulators and things like this entirely remotely.
Wow. Is it just, so you pay for access to just one organoid, or do you have any of them that are daisy chained or tied to each other as well to make a little network?
Well, daisy chaining, actually we did that. We did a number of experiments. This is called assembloids, actually. You take several
Assembloids.
Yeah, if you want to make it more complicated, it's easy, actually. So, for instance, we made organoids of striatum, an hippocampus, and cortical neurons. So 3 organoids. We put them with daisy chain, as we say, and then they will fuse together in a matter of days. Then you expect to have actually potentially the memory capabilities of the hippocampus, the capability to react to a reward of the striatum, and the capability to compute of the cortical neurons. So, okay.
So I don't know, how well are the mini brains working for computation? Are they as efficient as if it was just all biological, or are they a mixture of efficiency between in silico and biological?
So you don't want to use Wetware computers for number crunching. Okay, just don't do this. So if you run Windows on a Wetware computer, you're not going to be happy. Okay, I think to be.
What are you using it for? Like, are you using it for? Yeah, well, how are you using it then?
Well, first, people are using it for research. Okay, it's not in production like exploitation. Okay, stage yet. Okay, but what is going to be the main target is going to be AI, generative AI. Okay, each time. Well, most of the AI today works with simulations of neurons. Okay, so instead of simulating, let's use the real one. Okay, as simple as this. Very basic reasoning.
So something crazy. Has someone been able to? Like, what is the minimum number of organoids needed to create an LLM powered by organoids?
So no, I can give you some order of magnitudes. Like if you want to simulate one biological neurons, you would need several thousands of artificial neurons.
Really?
Yeah. So you can take the other way around, actually. You would potentially use way less biological neurons than artificial neurons, like thousands.
Oh, right. So I'm saying like ChatGPT or DeepSeek or whatever.
Yeah.
Could that be recreated and powered by organoids? And if so, how many would it take?
So this is really a bet, okay? Based on a number of applications, I would bet that you need way less neurons, okay? Biological neurons. And yes, I think it's absolutely possible to recreate a ChatGPT, and that makes sense.
That'll be a huge milestone, don't you think?
Yes, but it's a very meaningful milestone, and it's a very conservative milestone to claim that you are going to do processing of information using biological neurons, because nature has been doing this for 100 millions of years.
Right, but you wouldn't be able to explore the answer space normally. With these organoids, you're still using it as an LLM, not as like a regular biological brain. You're kind of using it for a different function, but it would be able to, if it can mimic ChatGPT, but be powered by, again, these organoids. Have you guys made a calculation of how many organoids would be needed?
Each organoid has, would say, like 10,000 of neurons, because these are mini brain organoids, okay? In order to do servers, we will not use organoids anymore. We'll use big nervous tissues of meters of size.
Oh, okay, because it's far more efficient than an organoid.
Yeah, it's going to be a totally different size.
Okay. I mean, maybe I don't know if this is ridiculous or not, but could you take the brain, a part of the brain from an animal that has passed away, and keep it alive and use that as, a whole set of ready to go neurons, like a neuronal cortex to power computation, like a rat brain, part of a rat brain?
Well, people have been doing works in electrophysiology, are doing exactly this for tens of years, okay, of studying primary cells of mammals, for instance. But this is absolutely not the direction that we are taking in our lab.
And I should have asked you before. I'm sorry. Go ahead. Tell me what you're working on.
You're right. This is called primary cells, and that could be done also, okay? But there is a problem with what you say, is that you actually kill a lot of animals, and there is a more modern way to do this, is actually to use stem cells. And then when you have stem cells, you can create millions of neurons in your lab.
Ah, yes. Okay.
Much more convenient, I can tell you.
So it'll be like a neuronal mass.
Yeah.
And that would be the organoid. It would be like a neuronoid or something like that, yeah?
Yeah, it will be a big mass of nervous tissue, yeah, ultimately, yes.
Have you made any of those yet?
No, the big ones, no. We made thousands of small ones of 1 millimeter of diameter. We still need to to master how to make them big. Big is easy, but big and living is more complicated.
To the blood supply, right?
Yes, the problem is vascularization. How do you bring...
Yes. No, sorry, go ahead, yes. Okay, I understand. Gotcha. How do you bring blood supply so that nothing is more than a millimeter away, let's say, from blood supply, or less than that, a micron away?
Yes, you're right. Yeah, that's the challenge.
Okay. So what's the major focus right now of your company? What are you guys trying to develop?
Well, there are different directions. First, we're using a lot of agentic AI, the traditional ones, to interact with the neurons. So basically, you pile up some black boxes, but agentic AI are able to. We give them API to interact directly with the neurons and read from the neurons, so they're able to perform things that we are not that fast and that smart. To modify the synaptic connections, you need to do a lot of things which are different from each organoid, and agentic AI are better than us, I think, for this. And it's not easy to figure out a universal algorithm. So far, so that's a very revolutionary approach. And we are also, please.
Do you start with a structure and then allow the AGI or the agentic AI to reorder the structure of it to make it more efficient? Is any of that going on? Or once the structure is set, it's static?
No. If you talk about structure, we talk about connectivity between neurons, okay? And when you change the connectivity between the neurons, you're not looking for efficiency at all, okay? This is the least of your worries. What you want is the capability to learn something. That means we're wiring the neurons, actually. This is what you do.
Like adjusting the weights in a neural network.
Yes, exactly this.
Yeah, so you're not changing the structure, but by changing the weights, you're changing how the calculations in each layer occur. I understand. That makes sense.
Well, actually, in biological neural networks, you have actually no weight as such. You have synaptic connections, and you have to change the synapses position in the network to change the weight.
Oh, wow. Biology is amazing. It's amazing how efficient and complex it is at the same time. It's unbelievable.
Yes, it is.
So, okay. So what would be like a dream result for your company in the next, couple of years? Is there one specific project that, if it gets completed, that you guys will be doing, be really contributing like crazy?
Well, yeah, we have to master training of the algorithms. We have to scale up in order to become a serious competitor to Amazon Web Services. And we are going to do it.
Okay. Well, very good, Fred. Where's the best way for people to keep tabs on what your companies are doing?
Oh, I think one good thing is to come on our Discord server. It's located directly from our website, and people are just free to come here, chat, and we will answer to every question.
Okay. Well, very good. I know, I started things late, but it still was a great short interview. So thank you so much, Fred. Appreciate you coming.
Thanks for your time and have a nice day.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Thank you for listening to the Good Question Podcast. Please email support@thegoodquestionpodcast.com if you have any referrals to great guests for us to interview. Visit thegoodquestionpodcast.com to hear more interviews. And please help us spread the word by rating and reviewing us on Apple Podcasts, iTunes, Spotify, YouTube, or wherever you listen to this podcast.